Okay, good morning. Welcome to the class. Today, let's have a look at the fourth lesson of chapter 5. We're going to have a look at the Cartesian vectors and their basic operations in two space. Okay, first of all, let's have a look at today's learning goals. After this lesson, you are expected to be able to understand the concepts of Cartesian vector, position vector, and unit vector in two space. Determine the magnitude and direction of a Cartesian vector in two space. Apply basic operations on Cartesian vectors such as addition, subtraction, and scalar multiplication in two space. Then determine the Cartesian vector between 2 points in the form of a position vector in two space. Last, use Cartesian vectors to solve some related problems in two space. Okay, so first of all, let's have a look at the concept of Cartesian vector and position vector. So suppose vector U is any vector in the plane with endpoints Q and R. We identify QR as a Cartesian vector because its endpoints can be defined using Cartesian coordinates. If we translate vector U so that its tail is at the origin here, O, then its head will be at some point P, A, B. Then we define this special Cartesian vector as the position vector, AB. So be careful with the symbol here. We use square brackets to distinguish between the point AB and the related position vector AB. So the position vector AB is also used to represent any vector with the same magnitude and direction as OP. Okay, so basically this is to say here in this diagram, vector QR and vector OP are equivalent. But vector OP is position vector of both of the two vectors. Okay, so I'll give you some time to have a look at these concepts. Make sure you understand their meaning, okay? Okay, are we clear now? Okay, then let's have a look at another concept, which is called unit vectors. So unit vectors in two space, vector I and vector J, are building blocks for Cartesian vectors. Unit vectors have magnitude 1 unit. Vector I, and vector J are special unit vectors that have their tails at the origin. The head of the vector I is on the x-axis at 0.10, and the head of vector J is on the y-axis at 0.01. In notation for Cartesian vectors, vector I equals 1, 0, and vector J equals 0, 1. Okay, so these are the concepts of unit vectors into space. Again, I'll give you some time to have a look at these concepts. Okay, have you finished? So if we resolve vector U into its horizontal and vertical vector components, then we get two vectors that add to vector U, right? From the graph on the left, sorry, not on this page, on the left. The magnitude of the horizontal vector is A, which is shown here. And it is collinear to vector I. Remember, vector I is a unit vector. Along the x-axis. Similarly, the magnitude of vertical vector is B, which is here. And it is collinear with the unit vector J along the x-axis or y-axis. Thus, we have the following relationship. Vector U equals A, which is a scalar, times unit vector I, plus another scalar B times unit vector J. Also note that A and B are the magnitudes of the vector U in the horizontal and vertical direction, respectively. Also from the graph, we know A times vector I equals A0. This is a representation for Cartesian vectors, right? And B times vector J can be represented using 0B. Since unit vector I equals 1, 0, and unit vector J equals 0, 1, we also have this relationship. A0 equals A times 1, 0, and 0B equals B times 1, 0, 1. This will be important in our later proofs. Thus, we have the following relationship. Vector U equals A0 plus B, 0B. Since U is AB, then we have AB equals A0 plus 0B. Therefore, for any vector AB, it can be written as the sum of its vertical and horizontal vector components, A0 and 0B. Okay, so have a look at these statements. Do you have any questions? All right, then next, let's have a look at how we can find this magnitude of a Cartesian vector. Any Cartesian vector, vector U equals V1, V2. Note that V1, V2 are the two components along the horizontal and vertical axis. Can be translated, so its head is at the origin 0, 0. And its tail is at some point V1, V2, right? To find the magnitude of the vector, use the formula for the distance between 2 points in 2 space. So the magnitude of vector V equals the difference between V1 and 0, then square, minus the squared difference of V2 and 0. So that equals the square root of V1 squared plus V2 squared. So basically that is to say, when you have a vector V1, V2, which is represented using a position vector, since magnitude of this vector equals square root of the squared first component plus the squared second component. Well, this is quite straightforward, right? You have any questions? Okay, if no questions, then let's have a look at the operation. Adding two Cartesian vectors. To add two Cartesian vectors, U, which is U1, U2, and V1, V2. use the unit vectors I and j. So note that u1 plus u plus v is u1, u2 plus v1, v2 as shown here. So this can be written as u1 0 plus 0 u2 plus v1 0 plus 0 v2, right? Because we can write u and v as sum of their horizontal and vertical vector components. Then that gives us u1 times I plus u2 times j plus u1 v1 times I plus v2 times j, because we can write the vector components in terms of I and j. I and j are the unit vectors along the two directions. Then we can collect like terms and factor, which gives us u1 plus v1i plus u2 plus v2j. Then we can substitute 1, 0, and 0, 1 for the two unit vectors, I and j. So that gives us u1 plus v1, 0, plus 0, then u2 plus v2, right? Then we can write the sum as a single vector, which gives us u1 plus v1, then u2 plus v2. So the two components for u plus v are u1 plus v1 and u2 plus v2. So that is the conclusion. When you add two Cartesian vectors, the x component, horizontal component, is the sum of the two horizontal components. The vertical component of the new vector is the sum of the two vertical components of the two vectors. You understand? Any questions? Okay, I'll give you some time to have a look at this. Okay, have you finished? So next, let's have a look at another operation, which is multiplying a Cartesian vector by a scalar. So we can let vector u equals u1, u2. u1, u2 are two components along the horizontal and vertical direction, and a real number k. Then k times vector u is k times u1, u2, this precision vector, right? So we can write vector u as a sum of its horizontal and vertical vector components. Then this gives us the expression here. Then write the vector components at multiples of unit vectors I and j. And we have this expression. Then expand this vector. This gives us k times u1 times unit vector I, and k times u2 times unit vector j. Then we can substitute 1, 0, and 0, 1 for vector I and j. Then expand. So that gives us the final result is the two components of the resultant vector is ku1 and ku2. So the conclusion is the product of a vector u1, u2, and a scalar k belongs to the real number set, is k times u equals ku1, ku2. ku1 and ku2 are the two components of the new vector. And also note that any scalar multiple ku of a vector u is collinear with u. We have already discussed this in geometric vectors, right? Any vector multiple, any scalar multiple ku of a vector u is collinear with the original vector u. Okay, again, I'll give you some time to have a look at this concept. All right, have you finished? Okay, then let's have a look at another operation, which is subtracting Cartesian vectors. So in previous lessons, we have learned that to subtract vectors is actually to add the opposite vector, right? Thus, for example, if u equals u1, u2, and v equals v1, v2, u minus v is actually u plus negative v, right? Then that equals u1, u2 plus negative v1, v2. Then the two components is u1 plus negative v1 and u2 plus negative v2. Therefore, the resultant vector is u1 minus v1, u2 minus v2. These are the two components of the new vector. Okay, any questions? No? Okay, then let's have a look at an example to check what we have learned so far. Operations with Cartesian vectors. Given vectors A, two components are 5, negative 7, and vector B, 2, 3, determine each of the following. First, question A, an expression for vector A in terms of its horizontal and vertical vector components. B, an expression for vector B in terms of unit vector I and J. C, 3A. D, A plus B. E, 2A minus 4B. F, two unit vectors collinear with A. And then magnitude of A minus B. Okay, I'll give you 5 minutes to consider this problem by yourself first. Then we'll have a look at the solution together, okay? You can start now. Okay, have you finished? And let's have a look at the solution together. Okay, first question. A can be represented using this form. Five, 0 plus 0, -7, right? For question B, vector B can be represented as 2i plus 3j. So note that the two components 2 and 3 means 2 times the unit vector in the first direction plus 3 times the unit vector in the second direction. Next, 3a is 3 times the position vector 5, -7. So that gives us 15, -21. Next one, a plus b. So we can just add the corresponding components. So that gives us 7, -4. Okay, next one is actually a linear linear combination of a and b, right? So 2a minus 4b. First of all, find 2a, which is 10, -14. Next, find 4b, which is 8, 12. Then calculate the difference, which gives us 2. That's the first component. -26 is the second component. Any questions? Okay, then next. Question F. A vector collinear with vector A is Ka, right? Where K belongs to the real number. So we can find a value for K such that Ka has magnitude 1. So magnitude Ka is magnitude of K times 5, -7. And that should equal 1. So we have square root of 5k squared plus -7k squared equals 1. So 74k squared equals 1. So we have k squared must equal 1 over 74. Therefore, k is either positive or -1 over square root of 74. Thus, two unit vectors collinear with A are either 5 over square root of 74, -7 over square root of 74, or -5 over square root of 74, and 7 over square root of 74. Any questions? Okay, then last question, G. The magnitude of A minus B. So first of all, we can find the vector corresponds to A minus B. So that is 5 minus 2, -7 minus 3. That gives us 3, -10. So the magnitude of 3, -10 equals square root of 3 squared plus -10 squared, which gives us square root of 109. All right, any questions? Okay, if no questions, let's continue. So next, let's have a look at the Cartesian vector between 2 points. If let P1 with coordinates x1 and y1 and point P2 with coordinates x2, y2 be 2 points on the coordinate plane. Thus, we have the vector P1, P2. So that's from P1 pointing towards P2 equals a vector P10 plus vector OP2, right? So We have already learned this in all previous lessons. Remember, we can find the resultant vector by using the triangle rules, right? Again, this equals OP2 minus OP1 because P10 is negative of OP1, right? So put the position vector for the two vectors. OP2 is actually x2, y2. OP1 is x1, y1, right? So this is the Cartesian vector form of these two vectors. Then we know P1, P2 can be expressed as x2 minus x1, y2 minus y1. So that this is two components of this vector. And to find the magnitude of P1, P2, we can use the formula for the distance between the 2 points. The magnitude of vector P1, P2 is the square root of the squared difference of x2 and x1 and square difference of y2 and y1. Understand? Okay, any questions? Okay, basically this is to say the position vector of P1, P2 is given by the coordinate of the terminal point minus the coordinate of the starting point, right? For both of the components. All right, if you don't have any questions, let's continue. So now let's have a look at an example. Find the coordinates and magnitude of each vector below. First, vector AB for point A is 1, 3, point B is 7, 2. Next, vector CD for C is -10, 0, and D is 0, 10. And then vector EF for E is 4, -3, and F is 1, -7. Okay, I'll give you 3 minutes to have a look at this question. Okay, have you finished? Well, let's have a look. Let's have a look at the solution together. Question 1, we know that vector AB is x2 minus x1, y2 minus y1, right? So x1, y1 is the starting point. x2, y2 is the terminal point. Therefore, vector AB is 1 minus 7, 2 minus 3. So the Cartesian form of vector AB is 6, negative 1. And then the magnitude of vector AB is square root of 6 squared plus negative 1 squared. This is square root of 37. And for question B and C, the method is the same, right? The vector CD is 0 minus 10, then 10 minus 0. So vector CD is 10, 10. And the magnitude is square root of 200. Vector EF is 1 minus 4, then negative 7 minus 3. So that gives us negative 3, negative 4. Then the magnitude of vector EF is square root of negative 3 squared plus negative 4 squared, which is 5. Okay, any questions here? All right, no questions. Let's have a look at the next, how to convert geometric vector to Cartesian vector. So to write a geometric vector V in Cartesian form, you need to use trigonometry. Previously, we found that the magnitude of the horizontal component is the magnitude of V times cosine theta. And the magnitude of the vertical component is the magnitude of V times sine theta, as shown here on the figure on the right, where theta is the angle the vector V makes with the horizontal or the positive x-axis. Thus, we can express vector V to magnitude of V times cosine theta and the magnitude of V times sine theta. So this is a Cartesian form of vector V. Understand? Okay, I'll give you some time to have a look at this concept. And after that, we'll do some practice. All right, then let's consider this example. We let vector U equals U1, U2, and vector V equals V1, V2, and vector W has components W1, W2. And let K, M, N belongs to the real number set. Can you prove each of the following properties using the Cartesian vectors? Okay, I'll give you 5 minutes to have a look at this example. All right, let's consider the solutions together. So for first property, note that the left side equals a vector with components u1 plus v1 and u2 plus v2, right? And the right side is a vector with components v1 plus u1 and v2 plus u2. So note that u1, u2, v1, v2 are scalars. Therefore, we know u1 plus v1 equals v1 plus u1. u2 plus v2 equals v2 plus u2. Therefore, we know left side equals the right side. So this statement has been proved. For property B, no, left side equals u1 plus v1 plus w1, and the second component is u2 plus v2 plus w2. Right side is u1 plus v1 plus w1, u2 plus v2 plus w2. Therefore, we have also proved left side equals the right side. For question C, the left side is ku1, ku2. The right side is u1k and u2k. Also note that u1, u2, and k are scalars. Therefore, we know left side equals the right side. Okay, property D, left side is kmu1, kmu2, right? And the right side is also kmu1 and kmu2. Therefore, we have proved left side equals the right side. Okay, property E, left side equals k times u1 plus v1, u2 plus v2, which gives us k times u1 plus v1, and k times u2 plus v2. The right side is k times u1 plus k times u1 u2 plus k times u1 v1 v2, which also gives us k times u1 v1 and k times u2 v2 as the two components. Therefore, we have proved left side equals the right side. Okay, for the last one, first check the left side. Left side equals k plus m times u1, u2. u1, u2 as two components. Then that equals k plus m times u1, then k plus m times u2. The right side is k times u1, u2 plus m times u1, u2, which also gives us k plus m u1, k plus m u2. Also note that km u1, u2 are scalars. Therefore, we have also proved left side equals the right side. Okay, any questions? Okay, if no questions, let's consider another example. You write a force of 200 newtons at 20 degrees to the horizontal in Cartesian form. Okay, I'll give you 3 minutes to have a look at this question. Okay, have we finished? Have a look at this together. So we can express the force F to the following two components. First, magnitude of F times cosine theta. Then the magnitude of F times sine theta. So that's the two components in the Cartesian vector. So that gives us 200 times cosine 20 degrees and the 200 times sine 20 degrees, which are approximately 187.9 and 68.4. So the force can be written in Cartesian form as approximately 187.9 and 68.4. Okay, any questions? All right, if no questions, let's have a look at last example. A ship's course is set to travel at 23 kilometers per hour relative to the water on a heading of 040 degrees. A current of 8 kilometers per hour is flowing from a bearing of 160 degrees. A, write each vector as a Cartesian vector. B, determine the resultant velocity of the ship. Again, I'll give you 5 minutes to have a look at this question by yourself. All right, have you finished? And let's have a look at the solution together. Okay, for question A, bearings are measured clockwise from the nose, right? You have already learned this in previous lessons, which is equivalent to clockwise from the positive y-axis. These have to be converted to angles with respect to the positive x-axis. The ship is traveling on a heading of 040 degrees, which is 40 degrees clockwise from the positive y-axis, as shown here in this graph. This is equivalent to an angle of 50 degrees from the positive x-axis. So let vector s represent the velocity of the ship. Then we know the velocity of the ship can be expressed as a Cartesian vector s equals 23 cosine 50 degrees, then 33 sine 50 degrees. The current is flowing from a bearing of 160 degrees, which is equivalent to an angle of 110 degrees with the positive x-axis, as shown here in the second graph on the bottom right. So if we let C represent the velocity of the current, then we know the velocity of the current can be expressed as C equals 8 times cosine 110 degrees, 8 times sine 110 degrees. Okay, that's for question A. Then in question B, determine the resultant velocity of the ship. Remember that in the previous step, we have expressed the velocity of the ship and velocity of the current in Cartesian form, right? So in question B, if we let R represent the resultant velocity, we know that the resultant velocity of the ship equals vector C plus vector C, right? So we can apply the addition for Cartesian vectors like this. We know the components of vector S is 23 cosine 50 degrees and 23 times sine 50 degrees. And the components for vector C is 8 times cosine 110 degrees and 8 times sine 110 degrees. So we can add the corresponding components together. That gives us approximately 12.048 and 25.137. So that's the vector R in Cartesian form. Then we can find the magnitude of the resultant vector velocity R. The magnitude of R is a square root of the squared x component plus squared y component. And this approximately is 27.875. Next, the bearing is an angle beta, as shown here in this figure on the right. The vector makes with the positive y-axis. From the graph, we know beta is arc tangent 12.048 over 25.137, which is approximately 25.6 degrees. Therefore, the conclusion is the ship is traveling at a velocity of approximately 27.9 kilometers per hour and at a bearing of 0 to 5.6 degrees. Okay, so have a look at this question. Any questions, just let me know, okay? Okay, if you don't have any questions, that's the end of today's lesson. Remember to complete your homework and submit your solutions onto Google Classroom before the deadline, okay? I'll see you next time. Bye.